Welcome to the first video in my series on proving the Twin Primes Conjecture. The blue graph that you see on the screen is a plot of the actual number of twin pairs within the first 2 billion primes. The number of twin pairs is plotted against the number of prime squares. Now you might be wondering, what would prompt me to plot the twin primes against the prime squares? The answer is that in the last few years I have made 4 discoveries regarding the twin primes that allow me to approximate the distribution of the twins with amazing precision. Here, for example, is the approximation for the same number of prime squares. As you can see, the approximation is so similar to the actuals that it obscures them entirely. Let's zoom in and look closer at the actuals and the approximation. Here is a zoomed view of the actuals. If we place the cursor over one of the data points, we will see the numbers behind it. This particular data point is the number of twin pairs up to the 13,821st prime square. The 13,821st prime is 149,689, while its square is 22,406,796,721. Since there are 57,129,440 twin pairs prior to that number, the data point indicates that there are that many twin primes prior to the 13,821st prime square. Now consider the approximation. Once again, the approximation is so similar to the actuals that it obscures the actuals' data points. Notice how the approximation duplicates the many anomalies in the twin primes distribution, as flagged by the arrows. You will also notice that the plot of the twins against the prime squares is exponential rather than logarithmic. And of course there are infinitely many prime squares. If the plot of the twins against an infinite set of numbers like the prime squares is exponential, what does that tell you about the distribution of the prime twins? So you can see where all of this is headed. If indeed I can make good on my claim that there is a mathematical link between the twins and the prime squares, then we will be very well positioned for crafting a proof that there are infinitely many twin primes. In these videos I will show you the 4 discoveries that I have made regarding the twin primes that make such a precise approximation possible. And oh yes, the short answer to why the twin primes are plotted against the number of prime squares is that the formula used to produce the approximation must add a new term every time a prime square is encountered. Consequently, it makes sense to calculate the data points at each prime square when the new term is added. In this video, we look at breakthrough discovery number 1, factor channels. Here is an example of factor channels. Along the left side we have the principal factors for this part of the number line, and of course above the number line we have the factor channels themselves with the blockages of the numbers along the number line in the form of colored rectangles. Definition 1. A factor channel for a given prime factor consists of a row located above the number line in which solid rectangles are placed above each multiple of the factor, beginning with its square, signifying that the multiple cannot be prime. We might think at first that this way of viewing primes is not very different from the usual view, but as we shall see, it leads to some rather startling discoveries. The first factor channel is for the number 2. For every number that has 2 as a factor, except 2 itself, we place a shaded rectangle above it in the 2-factor channel. Definition 2a. The principal factor for a given number n is the lowest prime factor q, such that q is greater than 1 but less than n. So for example, the number 6 has as its factors 1, 2, 3, and 6. The number 6 is disqualified from being the principal factor because it's not less than n. The number 1 is disqualified because it's not greater than 1. Since the number 2 is the lower of the 2 remaining factors, it's the principal factor. Thus we regard 3 as a secondary factor. Definition 2b. A secondary factor for a given number n is any prime factor s such that s is greater than q but less than n, where q is the principal factor. Each factor channel begins for a given principal factor with the factor's square. Thus in the 2-factor channel, the first shaded rectangle is placed above 4. The next factor channel is the 3-factor channel. In keeping with the square rule, the 3-factor channel properly begins at 9. This is because prior to 9, 3 cannot be a principal factor. It can only be a secondary. But starting at 9, the number 3 can act as a principal factor, since it does so in the factorization of 9 as 3 times 3. From that point forward, we place the shaded rectangles in the 3-factor channel for any number that has 3 as a factor. We do it even when 3 is a secondary factor, if the number is greater than 9, in order to follow the logic of the 3-factor channel. Thus, the 3-factor channel will have a rectangle every third position starting with 9. We can see quickly that 3 is the principal factor for 9, 15, and 21, but a secondary factor for 12 and 18. In the next example, we add the 5-factor channel beginning at 25. Again, we can see quickly that 5 is the principal factor for 25 and 35, but a secondary factor for 30. Now we add the 7-factor channel. If a factor channel can act as a number's principal factor, we say that the factor channel is operative for that number. So in this last example, the 7-factor channel is operative for 49 through 56, but not for 1 through 48. Definition 3a. A principal factor becomes operative at the point along the number line where it first meets the definition of a principal factor as opposed to a secondary factor. When there are no rectangles in the factor channels above a number, we say that there is a tunnel above the number, in which case the number is either prime or unity. It has no principal factor. We can see, for example, that there is no principal factor above 29. Therefore, we know that 29 is prime. The prime numbers and unity along the number line have been highlighted with a yellow background, and the number itself is in bold type. Non-primes except unity have a white background, and the number is in regular type. I have included unity with the primes since it also has a tunnel above it through the factor channels. As a result, its behavior frequently, though not always, resembles a prime's. Definition 3b. If a rectangle has been placed in a factor channel above a number, we say that the factor channel blocks the number from being prime. And definition 3c. We refer to a rectangle that has been placed in a factor channel above a number as a blockage. We can see that the 5-factor channel blocks 35 from being prime, while the 3-factor channel blocks 39. The factor channel does not indicate how many times a factor is used for a given number. The 2 blockages above 56, for instance, one in the 2 channel and one in the 7 channel, indicate only that 2 and 7 are factors. They do not indicate that 56 in fact has 2 as a factor 3 times. 2 times 2 times 2 times 7. The factor channels also do not indicate composite factors, since composites can never act as principal factors. Let's take a look at the first theorem that emerges from the factor channel concept. It's a stunner. Theorem 1a. Primes and multiples of 6. Every prime larger than 4 is a multiple of 6 plus or minus 1. Proof. We can see the truth of this theorem with a glance at the beginning of the number line with the 2-factor and 3-factor channels above it. The number line with the factor channels not only demonstrates the phenomenon, it explains it. The only positions that can be prime are the ones labeled A and C. All of the other positions, B, D, E, and F, are always blocked by either the 2-factor channel or the 3-factor channel, or both. Yet A through F repeats indefinitely. Here I have listed 3 repetitions of it, but note that the B position starts at 6, and every repetition of it is 6 positions farther down the number line. Thus primes larger than 4 can only be one less than a multiple of 6, that is, positions A sub 1, A sub 2 through A sub n, or one greater than a multiple of 6, that is, positions C sub 1, C sub 2 through C sub n as required. When I first came up with this theorem, I thought, surely this is known. It isn't. Fermat realized that all primes greater than 3 are a multiple of 4 plus or minus 3, but that's the closest anyone has come to the multiple of 6 plus or minus 1 rule. To see that rule, one really needs to think in terms of factor channels. In the event that a proof based on factor channels at this point is a bit hard to wrap one's head around, I have included a strictly arithmetic version that arrives at the same conclusion as Theorem 1a. I display it on the screen here for the viewer to examine. I will only mention for those who are not familiar with the notation that this notation is pronounced n is congruent to 1 modulo 6 and simply means that if we divide n by 6, it has a remainder of 1. The multiple of 6 plus or minus 1 rule leads us to a second theorem. This theorem too is a stunner and has great implications for understanding the twin primes. Definition 4. A pair of twin primes is any two prime numbers whose difference is 2. And while we're at it, let's formally define the conjecture that is the subject of these videos. Definition 5. The Twin Primes Conjecture states that there are infinitely many twin prime pairs. Theorem 1c. Twin primes and multiples of 6. For every pair of twin primes larger than 4, the first twin equals a multiple of 6 less 1, and the second twin equals the same multiple of 6 plus 1. Proof. By Theorem 1a, primes and multiples of 6, all primes larger than 4 are a multiple of 6 plus or minus 1. It follows then that for a pair of twin primes larger than 4, the first twin must precede a multiple of 6, and the second twin must follow it. If the first twin follows a multiple of 6, then the second twin, quote-unquote, would have to precede the next multiple of 6. In that case, however, the two primes would be separated by 4, not 2. The only way that two primes larger than 4 can be separated by 2, then, is if they straddle the same multiple of 6. Thus, for every pair of twin primes larger than 4, the first twin equals a multiple of 6 less 1, and the second twin equals the same multiple of 6 plus 1 as required. And finally, we have a third theorem that emerges from the factor channel concept. It may seem the least impressive of the three, but in fact it leads to the breakthrough discovery that makes the proof of the twin primes conjecture possible. Theorem 1e. The defining role of prime squares. Each principal factor becomes operative at its square. Definition 3a. A principal factor becomes operative at the point along the number line where it first meets the definition of a principal factor as opposed to a secondary factor. Proof. Let q, a member of the set of prime numbers, be arbitrary, and let n be a multiple of q, at which n will q become operative as a principal factor. There will be 4 cases. In cases 1 and 2, q can never be the principal factor. On the contrary, in those cases q can only be a secondary factor. Since the number that multiplies q is always smaller than q, either it or its principal factor will be the principal factor of n. In case 3, by contrast, q is always the principal factor. For case 3, n equals the square of q. Since q is the only prime factor of n, it must be the principal factor, whereas in case 4, q may or may not be the principal factor. Therefore, the lowest value of n at which q will be the principal factor will always be case 3, which is the square of q. Thus, each principal factor becomes operative at its square as required. As we shall see, this conclusion holds the key to proving the twin primes conjecture. In the next video, we learn how these 3 theorems lead to motif tables, which allow us to approximate the distribution of the twin primes with such amazing accuracy. If you care about mathematics and if you care about the twin primes conjecture, you won't want to miss it. I'll see you there. Be sure to subscribe and press the bell to ensure you are notified when the next video in the series becomes available.